and it's nice to see so many people here. Don't worry, I'm not one of the main speakers or anything, but instead of talking too much, I'd like to invite Mr. Dylan Andrew to come forward and give us his welcome address.
Hi, morning. Can everybody hear me? All right, welcome to Hack in the Box Security Conference 2004. I won't waste much time. Just like to thank our sponsors, ISS, Juniper Networks, NSS MSC, Transition Systems. I'd also like to thank our supporting organizations, the Malaysian Communications and Multimedia Commission, our partners in Bahrain, eSecurity Gulf Group, Roberto Priatoni from Zone H and the entire Zone H team, Six Square Singapore, X-Focus China, and also all our speakers for taking time out to fly down from around the world to be here today. I'd also like to thank the entire HITB crew for their efforts over the last 6 months to make this event possible, and without these guys, this would not have happened. Our first speaker for today, the keynote speaker for today, will be Mr. Theo raadt. I'm sure most of you are familiar with him. He's the creator and project leader of OpenBSD and OpenSSH, the most widely deployed open source software in the world. He'll be presenting his paper entitled Exploit Mitigation Techniques. So without further ado, I give you Mr. Theo raadt.
Good afternoon. So I'm going to talk about the exploit mitigation techniques that we've been doing in OpenBSD. And these are some general security technologies that could apply to other operating systems as well, very easily. But of course they happen in OpenBSD first. So let's talk about security from a kind of an abstract point of view. So an attacker, when he's playing with security problems on your machine, it does a couple of various things. He finds a bug, and since he understands the bug very well, he understands the side effects of this bug. The side effects are, for example, on a buffer overflow, it overwrites a bit too much memory for an integer signed integer versus unsigned integer overflow. It goes out of the range of the expected tests. But the real key over here is that because of the strict regularity of the system environment, the attacker is able to craft an exploit which grants him advantage. He's essentially converting the regularity of the system and the side effects together to get him this extended privilege. So maybe it's time for us to implement some technologies which will make it harder to write exploits. Much like in biological systems, the drugs that we use, some of them interact with the virus to prevent the virus from engaging a cell. Some of the drugs modify the cell behavior so the virus can't work there, and other ones modify the cell behavior once an attack has started. So we're going to try to do something very similar to the ecosystem in which these attackers are working. So our goals are to modify the Unix operating system to be more resilient against attack. Unix systems are designed according to a standard called the POSIX standard, and it delineates three things. Things we can't change in Unix, or it's not Unix. Things that we are allowed to change, these are things that are specifically specified, that the implementer has a number of options. And then there's some things which are left completely undefined or unspecified on purpose to make it easier for the implementer to do things. I'll give an example of a technical detail that implements in the C standard, not part of POSIX. In the C standard, char variables can be either signed or unsigned. This is a tremendous problem if you're actually trying to write secure software, but some processors are specifically designed for signed or unsigned chars. So it was left as open by the C developers, because otherwise there would be performance impacts. So for these three things, that's essentially POSIX, okay? But there's other standards as well, like there's BSD historical behaviors, there's System 5 historical behaviors, or just things that people have become used to how a system behaves. So we call those de facto standards. So we're going to be careful when we modify Unix. But our goals are essentially to not break any programs, and we're going to change anything that makes it hard for the attacker to break the system. And we're going to, very importantly, we're going to ensure that there's no performance hit or a very low performance hit from our change. So I'm going to proceed now with a list of mechanisms that we've implemented. And when I finish with a mechanism, I'll insert little bits of discussion as to where this, how these trends tie in together. So many of you are probably familiar with the mechanisms of a stack-based buffer overflow. But I'm going to start off with a very simple example for security technology. So in a stack-based buffer overflow, the attacker is overflowing this particular grayish buffer over there on top of the pink stack. The pink area of the stack is the downwards area that's used by the system. The white area down below is completely unused at this point. So with the overflow, the attacker is attempting to overwrite something like a return address, or maybe he's trying to attack the frame pointer. There's a number of objects he can attack on the frame to try to cause a side effect. The key point with this particular attack right here is that the pointer which the attacker is modifying, that's that red little value, it has to point into a specific fixed address on the stack to be able to allow the attacker to do this. And if, for example, the stack was slightly in a different place, or the buffer was at a different place, it would be hard for the attacker to do this. So this particular solution we're going to play with on the next slide, I'll show you in a moment, is to introduce a random sized gap on the stack to deviate the stack. So in the first example over here, we can see that the attacker has a pointer which points at the exact location where his code is. So he's able to actually do the exploit. But in the three successive cases, we have a randomly sized stack gap at the top. And this deviates the stack randomly on different code, on different executions of the same program. As a result, his pointer ends up pointing into an area where there isn't actually code. Now, some of you probably have played with exploits, and you know that you can take your exploitable code chunks and you can put no-ops and other sorts of things in there. But these are difficulties, and in some cases, the constraint of your buffer makes that difficult to do. So the cost of these changes is that it wasted most one page of real memory, because our programs are running in virtual memory. So at most one page is used. The administrator in OpenBSD is able to change this range for the stack gap, that's the speckled reddish area at the top, so that the maximum size of it is variable. For example, typically on some of our architectures we use 64K, and other ones we use 256K. And it's a 3-line change to the kernel. Okay. The key point here is this security technology makes some classes of security vulnerabilities completely infeasible to repeatedly, on a one-try basis, attack the program. There's no performance benefit to this. And I'd like to ask why the other vendors haven't picked up this 3-line change. It's astounding, isn't it? Why have we got an entire operating system ecosystem and people haven't implemented this thing, which in OpenBSD is now 4 years old? It's kind of crazy, isn't it? We'll go to the next technology that we have implemented for security purposes. Propolis is a Japanese fellow named Eto, who I actually managed to meet 3 days ago in Tokyo. It's a GC modification which modifies the compiler's output code. And the most common stack smashing problems result in program termination instead of exploitability. The compiler generates slightly different code. The prologue of function generation places a random value on the stack, and the epilogue checks to make sure it's still there. So to cut to the chase, it was integrated into OpenBSD a couple of years ago. Early on, it had quite a few bugs, but as our experience with it grew, we worked with the developer and started fixing these problems. There's some papers to be read over here if you're interested. The StackGuard paper is very interesting. because it shows an early implementation of such a technology to modify the stack, which turned out to be completely ineffective once attackers started looking at it. So we have this. I'll skip to the next slide. So your typical stack frame in a program looks like this. You have your arguments, your return address, your save frame pointer, your local arrays or pointers. What Propolis does, in the thing here I've shown, that it inserts a random value at the proper place in the stack, so that an overflow which happens from down below cannot actually succeed in overriding the save frame pointer or the return address. Okay? The second thing that it does is it reorganizes the local variables. It tries to make sure that the strings are placed closer to the canary, so that overriding the string variables will hit the canary. The result is that when an overflow happens and the function gets to its termination point, it will very quickly abort the program instead of continuing into code, into the attacker's payload. The performance impact of this change is 1.3%, and I think that's a worthwhile compromise to make for security. And we have found nothing which breaks as a result of this. All code continues executing. We have found bugs in software with these changes. In the last 2 months, there have been 2 security vulnerabilities in the X libraries, which have been found as a result of people diagnosing Propolis terminations of programs. So there's some tremendous security benefits of this, and has very low cost. Microsoft actually has a technology similar to this. It's the /GS option for their compiler. But an analysis has just been done by the developer of Propolis, and he's discovered that it's completely broken and ineffective. It doesn't actually work, and it's bypassable. He'll be presenting some of his work in Tokyo in about a month at the PACSEC conference, if any of you are going there or interested in seeing that. So every vendor should use a technology like this in any case. Okay, I'll go to another technology. Many of the bugs in our processes are exploitable because the memory that the processes run in has attributes that make certain pages both writable and executable. So what the attacker does, he ends up uploading code into memory and then controlling the program flow to end up executing his code. But we can do better than this. We can basically make the stack, which is the largest place, the most common place where people do these types of overflows, we can make it non-executable. Or we can go further, and we can apply a generic policy. This policy will be that nothing in the address space, which is writable, is also executable, or the other way around. Anything which is executable is not writable. And we're going to call this policy WXOR-X. And implementation of this depends on the architecture that we're talking about. I have a table here that shows a variety of architectures that have different abilities regarding the implementation of this. For example, on the SPARC 64, the Alpha, the AMD 64, the Itanium, and on HPPA machines, there actually is in the memory management unit a bit that's per page, which allows execution or non-execution. The i386 does not have a way to actually do this per page. But there's a code segment limit register, which allows us to draw a line in the address space. And I'll talk more about that in a couple of minutes. Or in newer versions of the processor, there's this PAE NX bit, and I'll talk about that. The PowerPC is similarly flawed. It only has an execute bit per segment, so pretty much 256 megabytes of memory. That's the only range. That's the only place where it actually has control over 256 meg of memory ranges. ARM CPUs used to actually have in the early versions an execute bit, but since Intel's been invading the market with their strong ARM, they've actually removed it. And there's some older processors I've listed here where essentially it's very difficult to do these tricks, or they're not very interesting processors. So OpenBSD has WXOR-X on a number of processors I list there, and a couple of them which we don't. So I'm going to go through the changes we made to the way that a process represents itself in memory. So we'll start off with static binaries in the Unix address space. And down below, you can actually see the program itself. It has a null page at the very bottom of memory, which is non-writable, non-executable, nothing. It's completely unmapped, so that you can catch null pointer dereferences. Followed by the code segment, which is readable and executable. The data segment, which is readable and writable, and has these things called CTORs and DTORs. I'll talk about those in a little bit. And the BSS segment, which is your zero initialized data. Up the top of the address space, we have the stack. And at the top of the stack, we actually have what's called the signal trampoline. The signal trampoline is used for returning from signal handlers. Now, right off the bat, we're going to try to solve the first problem. The stack has a W bit, as you can see, and the next bit. So this violates the policy that we're trying to establish. So what we're going to do is we're going to move the signal trampoline into a page of its own. So now we end up, as you can see on the right-hand side, with a stack segment that is writable and readable, but no longer executable. So we've crossed the first hurdle towards solving this problem. But we should really go look at what shared library executables look like. And at this moment, I should probably apologize because my slides start getting quite a bit hairier. So the static executable is on the left-hand side, and on the right-hand side, we have a dynamic executable. It has a shared library linker. Oh, you're one slide behind. No, yeah, forward. Forward. There. See, I told you it was complicated. He got scared. Okay. On the right-hand side, you can see a dynamic executable. The code segment and the stack are still in the same place, but in between we have two objects, the shared library linker, and for this program we only have one library, which is libc. In red and in purple or something, I've marked some problem areas that we're going to have to solve. So let's start looking, for example, at the red marked objects. What we have here is the data segment, which is supposed to only contain readable and writable objects, actually contains two new objects which we haven't talked about before, which have permissions that are incompatible with the permissions of what the data segment should have. The data segment should be read-write, but it contains this thing called a PLT. It's a shared library procedure linkage table, and it's used for calling sub-functions in another library. These are messy little details that you don't have to worry about what these objects are. But what I'm trying to point out to you is that we have an executable object sitting in the data segment. This is a violation of the rules. The second thing that we have is that we have some objects which are writable but don't need to be writable. For example, the global offset table and the PLT and the constructors and the deconstructors. So let's see if we can move these things around a little bit to try to reduce the privileges which we're granting here. So on this slide, you can see that we have moved the global offset table and the PLT into their own separate pages. They're no longer part of the data segment per se, but they are completely separate segments of the ELF binary format, and therefore they end up with separate pages of their own in the actual memory of the system. The global offset table is now just readable. Nothing ever writes to it. Well, actually, the shared library linker does. But the shared library linker adds write permission, changes an entry, and then deletes write permission again. Similarly, we've done the same change with the PLT. The PLT is readable and executable because it has to be, and the shared library linker will temporarily add write permission whenever it needs to make a change to it. So, as you can see now, a piece of the address space has become more secure. We'll move now to the red objects. The constructors and deconstructors were writable before. I'll explain what the deconstructors and constructors are for a moment. The constructors are used for example, by C++ to instantiate various thingies that it needs at C runtime. And the deconstructors are used at program exit to call some termination functions. So the deconstructors are the ones that we're really concerned about. An attacker could, for instance, go and modify the deconstructor table to contain pointers to his own execution code. but nothing ever modifies these tables. So what we've instead made is we've made the constructors read-only, and the deconstructors are read-only as well. So if you look at what we've got here on the right, we actually have, if you look at the RWX markers I have, we have no situation where a page of memory has both write permission and execute permission. And I've got a list of CPUs that this works on. So what we're really trying to say here is that there is no place for an attacker to place code and then jump to it in the entire address space. But you probably notice that most of you probably have i386 and Mac laptops, and both i386 and PowerPC are not there. So I'm going to go to the next slide and show you what we have to do to solve the problem on the i386. And if you thought this slide was complicated, wait till the next one. Okay. So these CPUs, like the i386, they don't have a concept of per-page execution, but they do have a concept of a range of execution. For example, what we've done with this model is we've made it so that code can only execute it during the red zone in the bottom of the address space. That's the 512 megabytes of address space. Above that line of 512, we don't allow code execution anymore. But obviously, when we're in a shared library environment, we have a sequence of objects that are executable, followed by a sequence of objects that require write permission, followed by a sequence of objects which have execution, followed by a sequence of objects which have write permission. So since we only have one line, there's no way to draw a line. As a result, we've rearranged executable. And since this is very confusing, I'm going to show this to you in a different way. Understand quickly that there's the main program, there's still ld.so, and there's the libc. So on the next slide, we can actually see what we've done. We have the bluish gray in the very, very middle, down below. That's the program. And we've split it so the code of the program sits low, and there's a 512 megabyte virtual gap until the writable components of the program are there. We've done the same thing with ld.so in purple and libc in red. Since we now have all of our writable components above 512 and all of our executable components below 512, we have succeeded at implementing the WXRX policy for the i386. Every single time I've presented this, someone in the audience has jumped up and told me this is insane, or I've seen heads shaking. But I'm not seeing any head shaking here, so I guess you guys have seen, some of you think this is actually worthwhile. So this required a lot of implementation. We had to modify the linker, the shared library linker as well. There were changes all over the entire address space. Now, newer i386 CPUs from AMD, now from Transmeta, the new VIA CPU is supposed to have it, and Intel keeps on advertising that they're working on it, even though we haven't even seen a prototype yet. I have a feature with something, okay, so we have what's called PAE. PAE is a 64-bit page table entry. Some machines have it. For example, my pretty much brand new IBM laptop with an Intel CPU does not even have PAE, and Intel tells us that they're actually going to be able to do NX when their flagship processor, the Pentium M, doesn't even have PAE. Yeah. They're a ways away from doing this. These new CPUs have what's an NX bit. It's a non-executable bit. And this works whether you're executing 32-bit instructions or 64-bit instructions. It's a separate 64-bit functionality for the memory management unit. It's not quite as good as an execute bit found on some CPU architectures, because you can make a page, the page has to be readable for it to be executable. You can't make a page that's executable but not readable. This is very interesting because we can finally have per-page executability on i386. So we'd like to use PAE, but are afraid of some complexity issues. Because we'd have to support two memory management units. The standard 32-bit legacy memory management unit would still have to be supported, but we'd also have to support the 64-bit mode as well. And as I just pointed out, my laptop doesn't have the 64-bit mode. So if we were to, for example, modify our code to run in PAE mode, we'd basically have to take 3/4 of the i386 machines on the planet and tell them that they can no longer run OpenBSD. So we have to support both. Now, supporting 2 MMU modes in a single architecture has been problematic for us before. The page map module, as I talk about over here. Oh, you're on the wrong slide again. Okay. Now you'll know where you're at. The page map module is used by the virtual memory management system to manage the page tables, the page table entries and everything. On a multiple MMU architecture like the Spark, where there's 3 CPU architectures, it takes 7,000 lines of code for the PMAP module. This ends up being approximately 1/3 of the machine-dependent code for that architecture. But on a typical architecture, a PMAP module is only 1,300 to 3,000 lines of code. So we're very concerned about the complexity of supporting 2 MMUs. Some systems, for example, Linux and FreeBSD, have support for PAE now. Not that they're actually using it. They're only using it to address more than 4 gigs of memory, potentially. They're not accessing it. They're not using it for an NX bit yet. They have PAE as a compile option. That's not feasible for us because that's not going to supply any security functionality by default. You're going to have to compile for security. That's a crazy posture. So we've been trying to convince vendors to implement a trivial 32-bit NX feature, but even though they're talking with us about it, they're not interested in implementing it. So eventually we're going to have to move towards doing NX. We have a WXRX mode for i386 that's good enough for what we're trying to do, but we'd like to actually do per page someday. It is also going to be faster. So the consequences of WXRX are that it makes the authoring of an exploit much more difficult because the attacker can't place code and then jump to it. We actually ended up, in this case, improving the performance on some architectures, especially on machines that have split TLBs, software TLBs and such. I think the Spark 64 is the best example, where we actually managed to get about a 5% performance improvement from implementing a security technology. This was quite surprising. And none of the architecture slowed down on implementing these features. And no software was broken with this change. So once in a while someone will point out, well, what about Java, which generates its own code and jumps to it? But this doesn't work anyways. You can't do self-modifying code on most modern CPUs. You can't on a PowerPC, or a MIPS, or an Alpha, or a Spark, or a Spark 64, or an Itanium. The only machine where you can really do it is an i386. And if you do such things, for example, on these newer i386s, you actually end up with a tremendous performance hit because they have to they flush their caches aggressively. So in a Unix system, the only way to properly do this is to use the msync and the mprotect system calls. So there's no breakage that has actually occurred here in the implementation. Any software which doesn't use those calls is broken already beforehand. So we had to go through a lot of contortions to implement this feature on an i386 for OpenBSD because we wanted to have the security technology even without using PAE. Other systems are going to try to implement this using PAE only, for example, Windows. But I want to point out a very important detail, that if you don't take every single page in the address space that's writable and make it executable, that means that you have one page in the address space that's writable and executable. And that's the page the attacker is going to use. So, for example, if Microsoft is moving towards implementing technology like this, but as far as I know, in SP2, there isn't a single process running that doesn't have a non-writable plus executable page. So therefore, they've kind of missed the point. So I'd just like to show a little diagram over here to show the software that we're actually running these days. This is Firefox, and you can see how many shared libraries this program has. Now, for each of these shared libraries, as a result of our changes, each of them is mapping 6 objects. So we end up with tremendous objects in the address space. 500 objects for Mozilla, 500 memory objects, data segments for each of these shared libraries, BSS segments for each of these shared libraries, a separate one for the constructors and deconstructors, for the PLTs, for the GOTs, for the code segment, And then the memory then the allocations start to happen on top of this. So when we initially implemented these changes to OpenBSD for WXRX, we ended up with a performance loss. Then we made some changes to our VM system with clever data structures to improve the performance, to get us back to this place where we were before. Then we disabled our code, which is WXRX, and we found that there was no performance increase. So there was an initial performance loss in our code, but we gained it back. And now disabling our security feature doesn't gain us any performance anymore. Okay, I'll talk about some more address space tweaks. So we were in shared library linker, ld.so, for some time because we were implementing these extra ELF objects for mapping. So having been there, let's see if we can do any more work while we're there. The first thing we're going to do is we're going to randomize the shared library order. We're going to map the shared libraries in a different order every single time the program starts execution. And this matters for programs that have a lot of shared libraries. As I showed in the previous slide, Mozilla has something like 28 libraries. And every single time you start the program, those 28 libraries are going to be mapped into the address space in a random order. We're also going to randomize the addresses for the shared libraries. Once we've randomized the order for the shared libraries, we're now going to put tiny little skews to shift them up or down in the address space. And we're wasting a little bit of virtual memory when we do this. But it's okay. What do we gain from this? We've now made it so that many objects in the address space are not where the attacker expects them to be. So if he needs to use something, because it's there in the address space, it isn't at the place where he expects it to. Every program execution has a different. So are you confused yet by all these obfuscations that we're doing? Because the attacker is. He's now having difficulty. Many times when you write an exploit, you're dealing with very fixed quantities that you have to generate very correct addresses for your buffer overflows. You have to hit just the right variable and change it. And it's now very difficult for the attacker because all the things in the process address space are moving around or being constrained. But there's more we can do, so I'm going to move on to some more things. We can mess up the address space more by randomizing the mmap system call, which is used by all sorts of programs to allocate or map files in the address space. So if the map fixed flag is not set, we're going to choose a random address in the address space. And the result is that each time you run the program, your object that you've mmapped moves around. And we're going to try to do the same thing with malloc. Because typically, on a regular system, when you call malloc and you allocate a piece of memory, it'll give you the same thing on program startup every single time. And when you call malloc again, you'll get another fixed address. This is very repetitive behavior. But if we make it random, let's see if we can do something better. So there's two types of objects that malloc handles. It handles things which are smaller than a page and things which are large, which are page size or larger. For the small object, malloc actually goes and allocates them out of these buckets that it maintains of freed and allocated objects. And what we're going to do is we're going to randomize which object it takes out of these buckets. And there's a malloc option that we have that turns this on. For the objects that are larger than a page, malloc just calls mmap. And since we've just randomized mmap, we end up with randomized objects there. Okay, do you understand where we're going with this? Like, how does the attacker now go and attack many of the objects in your heap? Every single time he tries to overwrite one of these objects, it's moved to a different place. All you have to do is restart the program. We can reduce write access. We've really been focusing on where the attacker can write code and execute. But can we make it so the attacker can't even write pieces of data that he's concerned about, which may change program flow control? So we start using a read-only data segment in our code. And anything which doesn't need to be executable or writable, we move into this read-only data segment. There's a piece of history attached here. The read-only data segment is actually a piece of ELF, of the ELF standard. It's been around since the beginning of the ELF standard. But no one's used it. Okay? It's kind of like everybody moved from the old Unix format to the a.out executable formats, and they moved to ELF and just used ELF as a new a.out. And they completely ignored this piece of functionality, which makes programs more secure. So this means that previously constant data was in a piece of was in memory in the text segment where it's executable, but we move it into a segment where it's not executable, it's only readable. Because in theory, any piece of data you put inside a program, data is code. The attacker can go and disassemble your data and see if it looks like instructions that are useful for him and can jump to them. Well, now he can't because they're not executable anymore. Okay, so that's the entire idea behind WXRX and the policy, that all objects should have the minimal set of permissions. And if we're talking minimal sets of permissions, the minimal set of permission is actually no permission. So the concept here is called guard pages. And some of you have probably used Electric Fence. It's a library, it's a malloc debug library you link with applications. It's a similar concept. So the idea is that we'll put unmapped objects all the way through the address space wherever we freely can, so that any unchecked overflow of memory will end up quickly hitting one of these objects. So we have a prototype where we implemented this inside malloc. Malloc, whenever it allocates an object, with an unmapped object after each one. And also in the mmap system call. But this is where we finally discovered a security feature which we couldn't actually turn on. We found out that most of the open source out there is absolute complete rotten garbage. It's completely normal for most people's software to access, i.e. read, 1 byte too far off of the allocated objects. And therefore they would, if the object that they allocated ends up butting up right against the very edge of the unmapped page, they access 1 byte too far, and the program gets terminated because it can't access there. As a result, even though we have this implemented, we can't turn it on. This makes me kind of sad because it's a really good security feature. But as we've been playing with it, we've pretty much discovered that we can't turn it on. We have some of the developers in OpenBSD who actually run with this, and they use it to find bugs. But we can't ship with it enabled. I'm going to talk about an architecture-specific security technology now. The existence of this security technology probably means that other similar, very clever ideas can be implemented on other architectures. Stack Ghost is something invented by a guy called Mike Franson. Some architectures for their registers use something called a register window. It's a register window architecture classification like Spark, Spark 64, AMD 29K, or Itanium. What happens with these registers is, in this case, on the Spark, there are 3 sets of registers called the ins, locals, and the outs. And every single time a function call happens to a function, the out registers, which are where you put your parameters that you're passing to the function, will become the in parameters of that function. And it's an architectural support feature. It's built into the entire architecture. This is the way you're supposed to use the architecture. So it's hard to do buffer overflows of registers. You can't really, that's not where you put your strings, so you can't overwrite them. But these processors have a limited amount of registers that they use for these ins, locals, and outs. And when they use too much of them on the processor, they end up calling spill and fill handlers inside the operating system to write these registers into memory. So eventually what happens is these registers containing your program counter or whatever else, your return addresses, end up in memory. And that's what the attacker attacks. So what Stack Ghost does is it modifies the spill and fill handlers. It XORs with a per process cookie, a random number, which is chosen at program startup time. It XORs the return address register when it transfers to and from memory. So the idea is that if an attacker goes and manages to overwrite the actual area of memory that will be loaded back into the registers, he cannot control the return address. So it's a pretty nerdy little feature, but it has no performance cost, and so we implemented it, and it makes certain types of attacks very difficult. Once again, it works kind of like ProPolice, but it's free, and it has no downside. Well, it had a downside. We actually had this in our source tree for about 2 years before the debugger support was implemented. And once that was implemented, we were able to enable it. And this is feasible on Itanium and SPARC64, and we're kind of looking at that a little bit. There's a lot of work to implement it, but we'd like to be able to do it there as well. A free security technology is a security technology you shouldn't avoid. Okay. I'm going to jump to a completely different way of protecting against security problems. So what an attacker does when he's attacking a program is he's trying to escalate his privilege. So how about if we take programs and we reduce the privilege that they actually have? So we're going to use, I'm going to define and describe two technologies that we do. One's called privilege revocation, and one's called privilege separation. And I provided a subset of the programs where we've actually done some of these things. And these are technologies we can use for either security programs or for daemons. So in privilege revocation, we take a particular program and we're going to modify it. Many programs, which are, for example, setuid programs, in this case we're going to use the example of ping. Ping starts up, allocates a sock raw, and then performs a task. And it continues performing that task as root. Therefore, way down the line while this program is running, if someone is this program is still running as root, and there's no need for it to be running as root. It already has the component it needs. It provides it with its capability. So we're going to use the privileges we have at startup to allocate this nasty, scary resource that the program uses to do its job. And then we're going to try to potentially jail this process into a CH root space or something, where this process is unable to do any harm. And then we're going to revoke the privileges. For example, now the program is actually running without any privileges in a jail, but it's still performing its task because it has a resource that does something nasty. So this is doable for simple programs. The key thing to notice over here is that this process is not running as root anymore, can no longer access the file system in a generic way, but it's still, in this case, for ping, has a sock raw. But at least we can look at sock raw as an object, and we can decide what the security considerations of it are. A sock raw can see ICMP packets on the net. The guy can insert certain types of packets onto the network. But it's not like he has root. He doesn't have the ability to write anywhere in the file system or modify programs. We've reduced the privilege of this program. Privilege separation is a similar concept. For programs that are more complicated, we sometimes end up having to do this. The idea here is that we're going to take a program that needs a privilege, and we're going to generate a pipe between two processes. And one of the processes is going to be jailed without any privilege, but he's going to be able to place requests to the little component of the process on the outside. And that little process is the one that's actually going to retain privilege and be able to do something on behalf of its child process. And I'm now going to show a couple examples of that. So one of them is our network time protocol daemon. What happens in this case is 1, 2, and 3 are the events that happen. First of all, our single process creates sockets out to a variety of children out on the, to a variety of network daemons out on the network. Second of all, a pipe is created to be used, and third, it's forked into 3 processes. The main process remains the master, and it is capable of doing the adjust time system call, which requires root, and because it's sitting outside in the regular file system, it's still able to do DNS requests and such, and so it does get host by name. The jailed child is the one that's actually going to run the major protocol of talking to all the children, deciding about the time offsets and such like that. And when it decides what the time offset is, it is capable of telling the parent, this is what you should set the time to. Or, I have a DNS, I have a host name I need to resolve, and I need to find out what the address is so I can do a connection to it. The result of this change is that approximately 90% of the daemon is running in a jail, completely privilege revoked. And there's only about, in this particular instance, I think there's 108 lines of code that is running as root. We only have 108 lines of code that we actually have to audit for security risk. That's the benefit of this. Okay. Now, unlike the previous technologies where we were changing the framework inside which processes operate, we're now actually taking the daemons themselves and making them run and modifying them for security. I'm going to show another example, something that you guys use all the time, I think. OpenSSH actually uses a variety of processes to be able to do its job. The main process at the very, very top spawns off for every single connection that comes into the SSH daemon, and it generates two privilege separated children. The first one is used just for authentication purposes, so that authentication doesn't run as root. The second component, once authentication is completed, is to run the entire session engine, not as root. And the idea here, and this is a very complicated example, and I can't explain to you exactly what all the messages are. There are 46 message types sent between the processes to be able to implement the full SSH scheme of things. And there's a paper you guys can read if you're interested in finding out more about this, so that you can go see if you can find some bugs or something. So I'm going to try to generate a little bit of a summary here, what we've talked about here. But the attacker now has the following problems that he has to overcome to be able to exploit. So because of ProPolice, he has to guess a 32-bit number that's on every single stack frame. Otherwise, he can't overwrite the frame pointer or the return address. ProPolice also provides a couple more things which I haven't listed here. Oh, I'd have listed. Flags and pointers are placed below the buffers in the stack frames so that he can't overwrite a buffer and modify the flags. He'll immediately run into either another buffer or into the canary. WXRX makes sure that there's nothing writable in the address space, it's just executable. The signal trampoline becomes non-writable. You can no longer modify it and then deliver a signal. The global offset table, the PLT, and the detours are not writable. So you can't even do an exit time attack of any sort. And constant data becomes non-executable. We have stuff happening on the Spark with a 32-bit number for every single return address. Our shared libraries move around all over the place so the attacker can't predict what he's attacking. malloc and mmap are randomizing our allocations so that the heap is protected to some degree. And many of the programs that are critically used by us have been modified to revoke their privilege or separated so that their privileges are at least contained in smaller self-contained pieces of code. And as I started my talk, the top of the stack is randomly biased to make it more difficult for the attacker even if he can get past all these problems. So in summary, we have implemented a number of low performance hits, in some cases non-existent, and in a few rare cases we've actually enhanced performance. And all the programs in OpenBSD continue to work fine. We have found problems using these technologies and then fixed them. So real bugs and real security problems have actually been found in pieces of software. And these changes really do stop attacks. And I should probably add now, why haven't all the other vendors been giving you these technologies? That's something I can't understand. Okay, so this is the end of my talk. Thank you very much. I'd like to add that I actually have about 30 OpenBSD CDs here, if any of you are interested, and you can find me in a couple minutes. Okay, I'll move to questions now, if there's any questions. No questions? No questions? Not one? Wow. Okay. Thank you very much.